What if everything you can see in the universe, every star, every planet, every galaxy shining in the cosmic darkness, is just a tiny fraction of what actually exists? What if the cosmos is dominated by something we cannot see, cannot touch, and barely understand? Something so mysterious that it defies our very definition of matter itself. You and I are about to embark on a journey into the invisible universe, where the greatest mystery in all of science awaits. We will follow the evidence, trace the clues, and explore the phantom scaffolding that holds reality together. Are you ready to see what cannot be seen? Look up at the night sky and you see stars. Thousands of them, scattered like diamonds against the velvet darkness. For most of human history, we believed this was the universe. What you see is what exists. The bright, the visible, the tangible. But what if I told you that everything you can see, from the smallest grain of sand to the largest galaxy, accounts for less than 5% of the universe? What fills the remaining 95%? This is not science fiction. This is the reality we inhabit, and it changes everything. The universe, as it turns out, is made of 3 fundamental components. About 5% is ordinary matter, the stuff of stars, planets, and us. Another 68% is something even stranger called dark energy, a mysterious force accelerating the expansion of space itself. But nestled between them is our focus tonight. 27% of everything that exists is dark matter. It does not emit light. It does not absorb light. It does not reflect light. It is, for all intents and purposes, completely invisible. Yet it is absolutely everywhere. How do we know something is there if we cannot see it? This question haunted scientists for decades. Imagine walking through a forest on a foggy morning. You cannot see the trees directly, but you can see their effects on the world around them. The way the fog swirls, the shadows they cast, the sounds that echo differently. Dark matter is like those invisible trees. We cannot see it directly, but we can observe its gravitational fingerprints throughout the cosmos. And those fingerprints are everywhere. Gravity is the key. Dark matter may not interact with light, but it does interact with gravity, and gravity shapes everything in the universe. When we look at how galaxies move, how galaxy clusters behave, how light bends through space, we see the unmistakable signature of something invisible, pulling, tugging, influencing everything around it. Dark matter is the hidden puppet master, moving the cosmic strings we can see. Tonight, we will trace those strings back to their source. This mystery began not with advanced technology or elaborate theories, but with a simple observation that did not make sense. In the early decades of the 20th century, astronomers began measuring how fast galaxies spin. They expected to find a certain pattern, a certain rhythm to the cosmic dance. What they found instead was something completely unexpected, something that would shake the foundations of our understanding. They found that galaxies were spinning far too fast. Something was wrong. Imagine a spinning disk. The outer edges should move slower than the center, just like the outer planets in our solar system orbit more slowly than the inner ones. This is basic physics confirmed by everything we see in nature. But when astronomers measured the rotation of spiral galaxies, they found the opposite. The outer edges were moving just as fast as the inner regions, sometimes even faster. This should be impossible. These galaxies should tear themselves apart. Yet they hold together serene and stable. There were only 2 possible explanations. Either our understanding of gravity was fundamentally wrong, or there was something else present, something we could not see, something massive, something providing the extra gravitational force needed to hold these galaxies together at such incredible speeds. The invisible scaffolding. the hidden architecture. The search for dark matter had begun, and it would take us to the very edge of human knowledge and beyond. Let us follow that journey together. As we prepare to dive deeper into this mystery, take a moment to consider what this means. You exist in a universe where most of reality is hidden from you. Your eyes evolved to see light, but light only reveals a fraction of what truly exists. The cosmos is far stranger, far more mysterious, far more profound than our ancestors could have imagined. And yet, through the power of observation, mathematics, and human curiosity, we have begun to map the invisible. We are learning to see the unseeable. Let us return to those spinning galaxies and understand exactly what astronomers discovered. Picture a spiral galaxy like our own Milky Way. It is a disk of hundreds of billions of stars, all orbiting around a common center. The stars near the center orbit quickly because they feel the strong gravitational pull of all the mass concentrated there. The stars farther out should orbit more slowly because they feel less gravitational force. This is exactly what happens in our solar system. But galaxies do not follow this rule. When astronomers measured the velocities of stars at different distances from galactic centers, they discovered something remarkable. The stars on the outer edges were moving just as fast as stars closer to the center, creating what we call a flat rotation curve. According to the laws of physics as we understood them, this should not be possible with the amount of visible matter alone. The outer stars should either slow down dramatically or fly away into intergalactic space. Yet there they remain, held in their orbits by something unseen. Think of it this way. If you swing a weight on a string in a circle above your head, the weight stays in its circular path because of the tension in the string pulling it inward. If you let go, the weight flies away. Galaxies are similar, but instead of a string, gravity provides the inward force. The puzzle was that the visible matter in galaxies did not provide enough gravity to keep those outer stars in orbit at the speeds observed. Something invisible had to be providing additional gravitational pull. This observation was not a one-time anomaly. Astronomers measured galaxy after galaxy, and the pattern held true. Spiral galaxies, elliptical galaxies, dwarf galaxies, all of them showed evidence of far more mass than could be accounted for by their visible stars, gas, and dust. The invisible matter was not just in one place or one type of galaxy. It appeared to be a universal phenomenon. Every galaxy in the universe seemed to be embedded in a massive halo of something we could not see. The implications were staggering. If every galaxy contained several times more dark matter than ordinary matter, then the universe we thought we knew was just the tip of the iceberg. Everything we can see, the entire visible cosmos, is merely floating on an ocean of invisible substance. The galaxies we observe are like foam on the surface of this dark ocean, their motions and structures dictated by currents we cannot perceive. We had discovered that the universe has an entire hidden layer of reality. Some scientists were skeptical. Perhaps our understanding of gravity itself was incomplete or incorrect at galactic scales. Perhaps Newton and Einstein had missed something. Modified theories of gravity were proposed, attempting to explain the observations without invoking invisible matter. But as evidence accumulated from multiple independent sources, the case for dark matter grew stronger and stronger. The dancing galaxies were trying to tell us something profound, and we were finally learning to listen to their message. By the late 20th century, the rotation curve problem had become one of the central mysteries of cosmology. Hundreds of galaxies had been measured, and the story was always the same. Too much speed, not enough visible mass, and the undeniable conclusion that something invisible and massive was present. Dark matter was no longer just a hypothesis. It was becoming a necessity, the only explanation that fit the data. But scientists wanted more than circumstantial evidence. They wanted to catch dark matter in the act. What we needed was a smoking gun, a piece of evidence so clear and undeniable that it would settle the question once and for all. We needed to see dark matter not just in one galaxy, but interacting with ordinary matter in a way that would reveal its presence beyond any doubt. And then, in a distant corner of the universe, two galaxy clusters collided in a cosmic catastrophe of unimaginable scale. When astronomers observed the aftermath, they saw something extraordinary. They saw dark matter and ordinary matter pulled apart from each other like witnesses to a crime separated for questioning. Imagine two of the largest structures in the universe, each containing thousands of galaxies, each with a combined mass of 1,000 trillion suns, hurtling toward each other through the void at millions of kilometers per hour. The collision, when it came, was not like two cars crashing. Galaxies within the clusters mostly pass through each other because the spaces between stars are so vast. But the enormous clouds of hot gas surrounding those galaxies, gas that glows with X-ray light, those clouds collided directly. And in that collision, we witnessed something remarkable. This cosmic wreck is known as the bullet cluster, named for the bullet-like shape of one of the colliding clusters. When astronomers studied it with X-ray telescopes, they saw the hot gas from both clusters slowed and heated by the collision, creating brilliant clouds of X-ray light. This was expected. Gas clouds collide and interact. But then they used a different technique called gravitational lensing to map where the mass actually was in the system. What they found shocked the scientific world. Let me explain gravitational lensing for a moment. Einstein showed us that massive objects bend space itself, and when light travels through bent space, its path curves. This means that a massive object like a galaxy cluster acts like a lens, bending and distorting the light from galaxies far behind it. By studying these distortions, we can map where the mass is, even if that mass is invisible. It is like seeing the shape of an invisible object by watching how it distorts the view behind it. A clever trick, revealing the unseeable. When scientists applied this technique to the bullet cluster, they found that most of the mass was not where the hot gas was. The visible X-ray gas had been slowed by the collision and remained near the center, but the gravitational lensing revealed that the majority of the mass had sailed right through, barely affected by the collision at all. The dark matter, being essentially collisionless, passed through the impact zone like two clouds of ghosts, each retaining its motion and structure. Mass and light had been separated. This was the smoking gun. Here was direct observational evidence that most of the mass in the universe does not interact with normal matter the way we expect. The galaxies and dark matter pass through each other because they interact only through gravity. The gas clouds collided and stuck together because they interact electromagnetically. The bullet cluster showed us a universe where two types of matter coexist but barely acknowledge each other, like two species living in the same forest but inhabiting different dimensions of reality. For scientists who had been skeptical about dark matter, the bullet cluster was a turning point. It was extremely difficult to explain this observation with modified gravity theories. The simplest and most natural explanation was that dark matter exists, it vastly outweighs normal matter, and it behaves differently during collisions. The evidence was written across the sky in letters 1,000,000 light-years tall. The universe was telling us plainly that it contains vast quantities of invisible substance, and we finally had the tools to read the message clearly. Since the bullet cluster, astronomers have observed other colliding clusters showing similar effects. Each one confirms the story. Dark matter is real, it is everywhere, and it dominates the mass budget of the universe. These collisions are like cosmic particle colliders, natural experiments happening at scales we could never hope to recreate in a laboratory. Each collision reveals the properties of dark matter, teaching us about its behavior, its distribution, and its role in shaping the cosmos we see. The universe itself has become our laboratory, but collision evidence is just one piece of the puzzle. Dark matter leaves its fingerprints in many other ways throughout the universe. Every observation adds another brushstroke to the portrait we are painting of the invisible cosmos. From the way light bends around clusters to the temperature fluctuations in the oldest light in the universe, dark matter's influence is everywhere if you know how to look. Let us continue our investigation, following the trail of evidence that leads us deeper into the mystery of the invisible scaffolding that holds reality together. One of the most powerful tools we have for detecting dark matter is also one of the most beautiful. Gravitational lensing transforms the universe into a cosmic art gallery where massive objects create stunning visual effects by bending light itself. When a galaxy cluster sits between us and more distant galaxies, its gravity warps the space through which light travels. The distant galaxies appear stretched, magnified, or multiplied into arcs and rings of light. These distortions are not optical illusions. They are the visible signature of invisible mass. Think of space-time as a flexible fabric, like a rubber sheet stretched tight. When you place a heavy ball on the sheet, it creates a dip, a depression. If you roll a marble past the ball, its path curves as it travels through the depression. Light behaves the same way. When it passes near a massive object, its path through space-time curves, causing the source of light to appear in a different position or shape than it actually is. The more massive the object, the stronger the lensing effect. And dark matter, being so massive, creates powerful lenses. By carefully measuring these lensing distortions across a galaxy cluster, we can reconstruct a map of where all the mass is, regardless of whether that mass emits light or not. It is like creating a topographic map of a landscape by watching how water flows across it, even if the landscape itself is shrouded in fog. What these maps reveal is astonishing. The distribution of mass extends far beyond the visible galaxies, forming vast halos that dwarf the luminous matter we can see. The galaxies are mere ornaments on a structure built of darkness. Some of the most spectacular lensing occurs when the alignment is nearly perfect, creating what astronomers call Einstein rings. These are complete or nearly complete circles of light formed when a distant galaxy, a massive foreground object, and Earth align almost exactly. The light from the distant galaxy is bent equally in all directions around the lens, creating a ring of light surrounding the lensing mass. These rings are rare and beautiful, cosmic bullseyes marking the locations of tremendous but invisible gravitational wells. Gravitational lensing has allowed us to weigh galaxy clusters with remarkable precision. Time and again, we find that the total mass is 5 to 10 times greater than the mass of all the visible matter combined. The stars, gas, dust, and planets account for only a fraction of what is actually there. The rest is dark matter, its presence revealed by the way it bends light from across the universe. In a very real sense, we are using light to illuminate the darkness, to make visible that which refuses to shine. But lensing reveals more than just the existence of dark matter. It tells us about its distribution, its density, and how it clumps together. We have learned that dark matter forms structures at every scale, from small clumps around individual galaxies to enormous filaments stretching between galaxy clusters. These structures trace out the skeleton of the universe, the hidden framework upon which everything else is built. When we map dark matter through lensing, we are seeing the invisible architecture that gives the cosmos its shape. One of the most ambitious projects in modern astronomy is weak lensing surveys. Unlike the dramatic arcs and rings of strong lensing, weak lensing produces only subtle distortions in galaxy shapes. But by measuring millions of galaxies across large swaths of sky, we can reconstruct the dark matter distribution across enormous cosmic volumes. These surveys are creating three-dimensional maps of the invisible universe, revealing how dark matter is distributed across billions of light-years of space and billions of years of cosmic time. What these maps show us is remarkable. Dark matter is not uniformly distributed. It clumps and clusters hierarchically, with small structures merging to form larger ones in an ongoing cosmic dance of gravitational assembly. The universe, when seen through the lens of dark matter, looks like a living organism, its structures growing and evolving over cosmic time. And ordinary matter, the stars and galaxies we can see, they simply follow the gravitational lead of the dark matter. They fall into its potential wells, they trace out its filaments, they light up the skeleton from within. Let us step back now and look at the universe as a whole, across its entire history from the Big Bang to the present day. What role has dark matter played in creating the cosmos we see around us? The answer is profound. Without dark matter, the universe would be a very different place. In fact, without dark matter, galaxies as we know them might not exist at all. Stars might never have gathered together in the quantities needed to form the brilliant spiral and elliptical galaxies we observe. The universe might have remained dark and formless forever. In the beginning, shortly after the Big Bang, the universe was remarkably smooth and uniform. Matter and energy were spread almost evenly throughout space, with only tiny fluctuations in density from place to place. These fluctuations were minuscule, variations of only 1 part in 100,000. Yet these tiny ripples contained the seeds of everything we see today, every galaxy, every star, every atom in your body. But these seeds needed help to grow. They needed gravitational amplification. They needed dark matter. Here is where dark matter becomes crucial. Ordinary matter in the early universe was tightly coupled to radiation, bouncing around in the intense light and heat, unable to collapse and clump together efficiently. But dark matter felt no such constraints. It did not interact with light. It began collapsing under its own gravity immediately, long before ordinary matter could. Dark matter started building structures first, creating gravitational wells that would later capture and hold ordinary matter. It laid the foundation, constructed the scaffolding, prepared the framework for everything that would follow. As the universe expanded and cooled, ordinary matter finally broke free from the radiation that had been buffeting it. This happened about 380,000 years after the Big Bang. At that moment, atoms formed for the first time, and light could travel freely through space. But by then, dark matter had already been working for hundreds of thousands of years, creating density contrasts, digging gravitational wells. When ordinary matter was finally free to move, it fell into these pre-existing dark matter structures like water flowing into riverbeds. From that point forward, dark matter and ordinary matter worked together in a cosmic partnership. Dark matter provided the gravitational glue, the skeleton, the framework. Ordinary matter provided the visibility, falling into dark matter halos and forming stars that would light up the universe. The first stars formed inside dark matter clumps. The first galaxies assembled where dark matter filaments intersected. Every luminous structure in the universe formed at a location predetermined by the distribution of dark matter. The invisible always came first. Computer simulations of cosmic structure formation have become one of our most powerful tools for understanding this process. Scientists can recreate the entire history of the universe in a computer, starting from those tiny initial fluctuations and letting gravity do its work over billions of simulated years. When they include dark matter in these simulations, the results match our observations beautifully. When they leave dark matter out, the simulations fail spectacularly. The virtual universe remains smooth and boring, nothing like the rich tapestry of galaxies we actually observe. These simulations reveal that dark matter structures form hierarchically. Small clumps form first, then merge to create larger structures, which merge again and again, building up the cosmic web we see today. This is called bottom-up structure formation. The smallest dark matter halos formed first in the early universe and gradually assembled into larger and larger structures over billions of years. Galaxies built themselves by merging, and so did galaxy clusters. The process continues even now. The universe is still building itself, still growing, still evolving. When we look at the largest scales, billions of light years across, the universe reveals its ultimate structure. Galaxies are not randomly distributed. They lie along filaments and sheets, surrounding vast empty voids. This cosmic web pattern emerges naturally from dark matter's gravitational collapse. The densest regions become galaxy clusters connected by filaments of dark matter along which galaxies form like beads on a string. The low-density regions become voids, nearly empty expanses of space. Dark matter carved out the architecture of existence itself, creating the stage on which the story of the universe unfolds. Every galaxy you have ever seen, including our own Milky Way, lives inside a dark matter halo. Imagine our galaxy as a luminous disk of stars about 100,000 light-years across, slowly rotating in space. Beautiful, majestic, containing hundreds of billions of stars. But this visible disk is just the heart of something much larger. Surrounding it, extending perhaps 10 times farther into space, is a vast spherical halo of dark matter. Our galaxy is like a pearl inside an invisible oyster shell, held and protected by this unseen cocoon. These dark matter halos are not solid objects with sharp edges. They are more like diffuse clouds of gravitating particles, densest at the center and gradually thinning out with distance. The total mass of the Milky Way's dark matter halo is estimated to be about 1 trillion times the mass of our Sun. Compare that to the visible stars, which total only about 200 billion solar masses. The dark matter outweighs the visible galaxy by a factor of 5 to 1. We live inside an invisible giant, barely aware of its presence. What is the dark matter halo made of? We know it must be particles of some kind, billions upon billions of them, perhaps trillions passing through every cubic meter of space, even passing through you as you listen to these words. They do not collide with ordinary matter. They feel no electromagnetic force. They are ghosts slipping through the walls of reality, present but intangible. The particles orbit the galactic center just like stars do, but their orbits are more chaotic, less organized. They form a diffuse cloud rather than a neat disk. The halo serves a crucial function. Its gravity holds the galaxy together. Without the halo, the visible stars would have far less gravitational binding. The galaxy would be more fragile, more easily disrupted. Some stars would escape into intergalactic space. The galaxy might never have formed a stable structure in the first place. The dark matter halo is the foundation upon which our galaxy was built and the glue that keeps it intact. It is simultaneously cradle and guardian, the hidden parent of every star in the visible disk. As we observe other galaxies, we find the same pattern everywhere. Every galaxy has its dark matter halo. Dwarf galaxies have smaller halos. Giant elliptical galaxies have enormous halos. The relationship between the visible galaxy and its dark halo seems to follow predictable patterns, suggesting that a fundamental connection exists between how much dark matter a halo contains and what kind of galaxy forms within it. The visible universe dances to the tune played by its invisible partner. Interestingly, computer simulations predict that dark matter halos should contain numerous subhalos, smaller clumps of dark matter orbiting within the larger halo structure. These subhalos might outnumber visible satellite galaxies by hundreds to 1. If this is true, then space around our galaxy is teeming with invisible structures, dark matter clumps perhaps containing no stars at all, invisible satellites orbiting the Milky Way in silence and darkness. A hidden population waiting to be discovered through their gravitational effects. The halo structure also explains another mystery. Our galaxy has been cannibalizing smaller galaxies for billions of years. Dwarf galaxies that venture too close are torn apart by tidal forces and their stars absorbed into the Milky Way. We can see the streams of stars from these disrupted galaxies stretching across the sky. But the process should have been even more destructive without dark matter halos protecting both the Milky Way and its victims. The halos allow galaxies to survive close encounters that would otherwise destroy them. Standing here on Earth, you might wonder what it means to be inside a dark matter halo. In a very real sense, we are swimming through an ocean of dark matter particles right now. They pass through the Earth, through the walls of your home, through your body, constantly and without interaction. Estimates suggest that thousands of dark matter particles pass through every square centimeter of your body, every second. You are immersed in an invisible sea, a phantom realm that surrounds and permeates everything, yet remains eternally beyond your senses. We know dark matter exists. We know how much of it there is. We know where it is, but we do not know what it is. This is perhaps the most profound mystery in all of physics. What is this substance that makes up most of the matter in the universe? What are the particles that compose it? What are their properties? For decades, physicists have been hunting for the answer, deploying some of the most sensitive instruments ever created, searching deep underground, looking to the skies, and smashing particles together in enormous accelerators. The search for dark matter has become one of the great quests of our time. What properties must a dark matter particle have? We know several things. It must be stable, or at least very long-lived, surviving since the Big Bang until today. It must interact only weakly with ordinary matter, explaining why we have not detected it yet despite its abundance. It must be relatively slow-moving, or cold in physics terminology, to explain how structures formed in the universe. And it must exist in sufficient quantities to account for the gravitational effects we observe. These constraints guide the search, narrowing the possibilities. The leading candidate for many years has been a hypothetical particle called a WIMP, which stands for Weakly Interacting Massive Particle. These particles, if they exist, would have masses perhaps tens or hundreds of times heavier than a proton. They would interact through gravity and possibly through the weak nuclear force, but not through electromagnetism. This would make them extraordinarily difficult to detect. WIMP could pass through an entire planet without ever hitting an atom. But occasionally, very rarely, one might collide with a nucleus, and that collision could potentially be detected. This is the principle behind direct detection experiments. Scientists fill large tanks with ultra-pure materials, often liquid xenon or argon, cooled to extremely low temperatures. They place these tanks deep underground to shield them from cosmic rays and other background radiation. Then they wait, monitoring the detectors for the telltale sign of a dark matter particle colliding with an atomic nucleus. It is like fishing in the dark for invisible fish, hoping for the tiniest tug on your line. Patience and extreme sensitivity are required. These experiments are marvels of engineering. The detectors are so sensitive they can register the impact of a single subatomic particle. The tanks are shielded by layers of lead and water to block background radiation. The materials are selected and purified to eliminate even trace amounts of radioactive contaminants. The entire apparatus is placed kilometers underground in old mines or specially excavated caverns. Everything is designed to create the quietest possible environment, a silence so profound that even the whisper of a dark matter interaction might be heard. Despite decades of effort and increasingly sensitive detectors, WIMPs have not been conclusively detected. Some experiments have reported tantalizing signals that might be dark matter, but these have not been confirmed by other experiments. The lack of detection does not mean dark matter does not exist. It might simply mean that WIMPs are not the answer, or that their interaction rate is even lower than predicted. The search continues, pushing to ever greater sensitivities, exploring different target materials, and refining theoretical predictions. Another approach is indirect detection. If dark matter particles can interact with each other, they might occasionally annihilate when they meet, converting their mass into energy and producing standard model particles we can detect. This might happen in regions where dark matter is particularly dense, such as the centers of galaxies or inside the Sun. Telescopes search for excess gamma rays, neutrinos, or other particles coming from these regions, hoping to catch the signature of dark matter annihilation. It is a different kind of fishing, looking for the flash when two invisible fish collide. Space-based telescopes and ground-based observatories monitor the sky for these signals. The Fermi Gamma Ray Space Telescope has mapped the gamma ray sky in unprecedented detail. Neutrino detectors buried in ice at the South Pole watch for unusual neutrino signals from the Sun or galactic center. So far, no definitive detection has been made, but interesting hints and anomalies keep appearing, each one spurring more detailed investigations. The indirect search complements direct detection, attacking the problem from multiple angles, increasing the chances that we will eventually corner our elusive quarry. If not WIMPs, then what? The universe of possible dark matter candidates is vast and strange. Physicists have proposed dozens of different particles, each with unique properties and detection challenges. Some are heavy, some are light. Some interact rarely, others even more rarely. Some come from established physics theories, others require entirely new frameworks. Let us explore this zoo of possibilities, this parade of phantom particles that might constitute the invisible scaffolding of reality. Each candidate tells a different story about the fundamental nature of the cosmos. One intriguing candidate is the axion, a particle originally proposed to solve a different problem in physics, but which turned out to have properties perfect for dark matter. Duptions would be extraordinarily light, perhaps a trillion times lighter than an electron, and they would be produced in tremendous numbers in the early universe. Instead of individual heavy particles, dark matter might be an ocean of countless ultralight axions, behaving more like a wave than like particles. This would require entirely different detection strategies, sensing not individual collisions but subtle electromagnetic effects. Axion detectors are strange and wonderful devices. They typically consist of a cavity placed inside a strong magnetic field. If axions pass through the cavity, the magnetic field would occasionally convert them into photons at a very specific frequency. By tuning the cavity and listening for photons at that frequency, experimenters hope to hear the whisper of axion dark matter. It is like building a radio to receive signals from an unknown station broadcasting on an unknown frequency. You tune slowly through the dial, listening carefully, hoping to catch something in the static. Another candidate is the sterile neutrino, a hypothetical cousin to the known neutrinos, but even more reclusive. Ordinary neutrinos barely interact with matter, earning them the nickname ghost particles. Sterile neutrinos would interact even less, perhaps only through gravity. If they exist with the right mass and abundance, they could account for dark matter. Searchers look for slight distortions in the spectrum of X-rays from galaxy clusters or for subtle effects in neutrino oscillation experiments. Finding sterile neutrinos would connect dark matter to the known particle physics framework in surprising ways. Then there are more exotic possibilities. Primordial black holes, formed in the first moments after the Big Bang, might constitute some or all of dark matter. These would not be black holes from collapsed stars, but tiny, dense objects created by fluctuations in the early universe. They could range from the mass of a mountain to many times the mass of the Sun. Detecting them requires looking for gravitational lensing events when they pass in front of distant stars. Several such events have been observed, but whether they account for all dark matter remains uncertain. Some theories propose that dark matter consists of macroscopic objects made of strange quark matter, called strangelets, or nuggets of nuclear density material. Others suggest it could be topological defects in spacetime itself, like cosmic strings or domain walls, relics from phase transitions in the early universe. Each idea pushes the boundaries of physics in different directions. Each requires different observations and experiments to test. The search for dark matter has become a search through a vast landscape of theoretical possibilities, each as strange as the last. Particle accelerators like the Large Hadron Collider also play a role. If dark matter particles can be created in high-energy collisions, they would immediately escape the detector without leaving a trace. But their presence could be inferred from missing energy and momentum in collision events. Physicists look for events where particles fly out in one direction, but the total energy does not balance, suggesting that invisible particles carried some energy away. So far, no definitive signal has appeared, but each collision event constrains the possibilities, ruling out certain dark matter models. The fact that we have not yet identified dark matter is humbling, but also exciting. It tells us that nature still holds profound secrets, that our understanding of physics remains incomplete. The answer, when it comes, will likely reshape our view of the universe fundamentally. Every negative result is valuable, eliminating possibilities and guiding future searches. Every new experiment pushes our technological capabilities to new limits. The search for dark matter is not just about finding a particle. It is about understanding the cosmos at its deepest level, and that quest continues with renewed vigor. Let us travel back in time now, to when the universe was just 380,000 years old. At that moment, the cosmos underwent a transformation. It had been opaque, filled with hot plasma where photons scattered constantly off free electrons. Then, as temperatures dropped, electrons combined with protons to form neutral atoms. Suddenly, light could travel freely. The universe became transparent. The light released at that moment has been traveling through space ever since, cooled by cosmic expansion into microwave radiation. We call it the cosmic microwave background, and it is a treasure map to the universe's secrets. When we observe the cosmic microwave background with sensitive instruments, we see tiny temperature variations across the sky. Some regions are slightly warmer, others slightly cooler, by only millionths of a degree. These variations are not random. They encode information about the density of matter and energy when the light was released. They are baby pictures of the universe, showing the seeds that would grow into galaxies and clusters. And remarkably, the pattern of these variations tells us about dark matter with extraordinary precision. The temperature fluctuations in the cosmic microwave background have a characteristic pattern. There are variations at different angular scales, and the relative strength of these scales depends sensitively on the composition of the universe. Ordinary matter, dark matter, and dark energy each affect the pattern differently. By measuring the pattern precisely and comparing it to theoretical predictions, we can determine how much of each component exists. It is like analyzing a musical chord to determine which notes are present and how loud each one is. What the cosmic microwave background tells us is remarkable. The universe is flat geometrically. It contains about 68% dark energy, 27% dark matter, and only 5% ordinary matter. These numbers are measured with extraordinary precision, typically to better than 1% accuracy. This is cosmology as a precision science, and it all comes from carefully analyzing the faint patterns in ancient light. The cosmic microwave background provides independent confirmation of everything we have learned from galaxy rotation curves, gravitational lensing, and structure formation. The pattern of fluctuations tells us that dark matter must have been moving slowly when structures formed. Fast-moving particles would have smoothed out small-scale structures. The fact that we see fluctuations at all scales means dark matter is cold, moving at speeds much less than the speed of light. This eliminates many possible dark matter candidates, such as ordinary neutrinos, which move too fast. The baby pictures of the universe are telling us what the dark matter must be like. Missions like COBE, WMAP, and Planck have mapped the cosmic microwave background with ever-increasing precision. Each mission revealed finer details in the ancient light, measuring smaller angular scales and fainter signals. The Planck satellite, which completed observations in 2013, produced the definitive map of the microwave background, seeing details no previous instrument could detect. The precision of these measurements is astonishing. We know the age of the universe to within 1%. We know its composition to exquisite accuracy. Ancient photons have taught us the deepest truths. The agreement between different lines of evidence is striking and reassuring. Galaxy rotation curves tell us dark matter exists. Gravitational lensing maps where it is. Structure formation shows what it does. And the cosmic microwave background measures how much there is with incredible precision. All of these independent observations point to the same conclusion. Dark matter is real. It dominates the universe's matter budget, and it shaped cosmic evolution. The convergence of evidence from such diverse sources gives us confidence that we are on the right track. Looking at the cosmic microwave background is looking back to the dawn of time, seeing the universe when it was young, simple, and almost perfectly smooth. Those tiny ripples in the primordial plasma were the seeds of everything we see today. Every galaxy, every star, every planet, every atom in your body traces its existence back to those quantum fluctuations in the early universe, amplified by dark matter's gravity into the rich cosmic tapestry we inhabit. You are looking at your own origin story, written in microwave light 13.8 billion years old. We stand now at an exciting moment in the search for dark matter. New experiments are coming online with unprecedented sensitivity. New telescopes are observing the universe in wavelengths never before explored. New theoretical ideas are expanding the landscape of possibilities. The next decade may bring the breakthrough we have been seeking, the moment when we finally identify the particle or particles that constitute dark matter. Or it may deepen the mystery, revealing that dark matter is even stranger than we imagined. Either outcome would be transformative for physics. Next generation, direct detection experiments are being designed with target masses measured in tons rather than kilograms. They will be even more sensitive, able to detect even rarer interactions. If dark matter interacts with ordinary matter at all, even extraordinarily weakly, these experiments should find it. Similarly, indirect detection efforts are expanding with larger detectors and improved analysis techniques. The net is tightening. The parameter space where dark matter can hide is shrinking. We are closing in on the answer, methodically eliminating possibilities until truth reveals itself. New astronomical surveys are mapping the universe in unprecedented detail. Projects like the Vera Rubin Observatory will observe billions of galaxies, measuring their shapes and positions to create the most detailed map of dark matter ever made. The Euclid Space Telescope will trace the distribution of dark matter across cosmic time. The James Webb Space Telescope, peering deeper into space than ever before, may reveal clues in the formation of the first galaxies where dark matter played its crucial role. Every new observation is a potential window into the dark sector. Theoretical physicists continue to explore new ideas. What if dark matter is not one type of particle, but a whole dark sector, a hidden realm of multiple particle types interacting with each other, but barely with us? What if dark matter can decay slowly over cosmic time, producing signals we might detect? What if it has unexpected properties like self-interaction, causing dark matter halos to behave differently than predicted? These questions drive new calculations, new simulations, and new observational strategies. Theory and observation dance together, each inspiring the other. There is even the possibility that dark matter is not a particle at all, but rather a modification of space-time or gravity itself. Perhaps Einstein's general relativity requires correction at certain scales or in certain regimes. Modified gravity theories have been developed that can explain some observations without dark matter. However, these theories struggle to explain the full range of evidence, particularly the bullet cluster and the cosmic microwave background. Most physicists favor the dark matter explanation, but the alternative ideas remain active areas of research, reminding us to question our assumptions. Machine learning and artificial intelligence are becoming powerful tools in the search. Neural networks can analyze vast datasets from sky surveys, finding subtle patterns humans might miss. They can optimize detector designs, maximizing sensitivity while minimizing background noise. They can simulate universes with different dark matter properties, comparing billions of possible scenarios to observations. The fusion of astrophysics with computer science is opening new frontiers, allowing us to explore the dark matter parameter space with unprecedented efficiency and creativity. Whatever the ultimate answer, the search for dark matter is driving innovation across physics and astronomy. New detector technologies developed for dark matter searches find applications in medical imaging, environmental monitoring, and national security. Analytical techniques pioneered in cosmology spread to other fields. Young scientists entering the field bring fresh perspectives and new ideas. The quest has become a training ground for the next generation of physicists, inspiring thousands to pursue fundamental questions about nature. The journey matters as much as the destination. As we push deeper into the mystery, we must remain open to surprises. The history of physics teaches us that nature is often more imaginative than we are. Black holes, quantum mechanics, relativity, the expansion of the universe, each of these discoveries challenged our intuitions and expanded our understanding in unexpected ways. Dark matter may yet surprise us, revealing connections to other mysteries we have not anticipated. Perhaps it is tied to the matter, antimatter asymmetry, or to the nature of dark energy, or to physics beyond the standard model in ways we cannot yet imagine. Let us return to where we began and consider what it means to live in a universe dominated by darkness. You wake each morning on a planet made of ordinary matter, orbiting a star made of ordinary matter, in a galaxy held together by dark matter. The atoms in your body are rare exceptions in a cosmos composed mostly of something else. We are, in a profound sense, the minority. The universe belongs to the dark sector. We are visitors in a realm that is not fundamentally ours, temporary patterns in a vast ocean of invisible substance. This realization is simultaneously humbling and elevating. Humbling because we are forced to admit how limited our senses are, how much of reality we cannot directly perceive. We evolved to navigate a specific environment, to see certain wavelengths of light, to interact with matter electromagnetically. Our biology is optimized for survival in our particular niche, not for comprehending the cosmos in its entirety. We are like fish that have just discovered the existence of air, realizing that the ocean is not all there is. Yet the discovery is also elevating because it demonstrates the power of human intellect. Without ever touching a dark matter particle, without ever seeing one directly, we have deduced its existence, measured its abundance, mapped its distribution, and understood its role in cosmic history. We accomplished this through observation, reasoning, mathematics, and the scientific method. We extended our senses through instruments, we amplified our understanding through theory, and we reached beyond our limitations to grasp truths about the universe that evolution never prepared us to understand. Dark matter also invites philosophical reflection. What is real? We typically define reality as that which we can see, touch, or directly measure. But dark matter shows us that the universe contains entities profoundly real in their effects, yet forever beyond our direct experience. They are not illusions or abstract concepts, but concrete physical things with measurable properties. Reality, it turns out, is larger than perception. The universe does not care whether we can sense something. It exists regardless, following its own laws, indifferent to our limitations. Consider the implications for our sense of place in the cosmos. We already knew that Earth is not the center of the universe, that our sun is an ordinary star among hundreds of billions, that our galaxy is one among trillions. Now we learn that even the matter we are made of is not the dominant form of matter in existence. We are not just cosmically small in space and time. We are small in substance, made of the rare stuff, while most of the universe consists of something entirely different. Each discovery chips away at our centrality, yet somehow enriches our understanding. There is beauty in this perspective. Beauty in the recognition that the universe is stranger and more wonderful than we imagined. Beauty in the elegant mathematics that describes dark matter's influence. Beauty in the cosmic web it creates, that magnificent architecture of filaments and voids. Beauty in the fact that something so hidden can be revealed through careful thought and observation. The mystery of dark matter is not a flaw or gap in our knowledge. It is an invitation to wonder, a reminder that nature still holds secrets, that there are still dragons at the edges of the map. Perhaps someday we will identify the dark matter particle. Perhaps we will learn to detect and manipulate it. Perhaps future civilizations will develop technologies based on dark matter, interacting with that hidden sector in ways we cannot yet imagine. Or perhaps dark matter will remain forever beyond our direct grasp, known only by its gravitational effects, a permanent reminder of the boundaries of human knowledge. Either way, the search has already transformed our understanding of the universe and our place within it. As you go about your life, remember that you are part of this cosmic story. Dark matter passes through you constantly, billions of particles every second, connecting you physically to the invisible universe. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stars that formed in dark matter halos. Your existence is tied to the dark matter through the entire history of cosmic structure formation. You are not separate from this mystery. You are embedded in it. A conscious pattern temporarily emerged from the interplay of dark and light, matter and energy, asking questions about its own origins. Our journey into the invisible universe ends here, but the search continues. The mystery of dark matter remains one of the great unsolved problems in all of science, and its resolution will transform our understanding of reality itself. As you drift towards sleep or simply sit in quiet contemplation, think about the vast invisible ocean in which we swim, the scaffolding that holds the cosmos together, the darkness that makes the light possible. We live in a universe far stranger and more magnificent than our ancestors dreamed. What other secrets await us in the darkness? What other invisible wonders surround us even now, waiting to be discovered? The cosmos is full of mysteries, and each one is an invitation to look deeper, to question more boldly, to reach beyond what we can see toward what we can imagine. Until we meet again, keep looking up, keep wondering, and keep seeking the light in the darkness.